So hello, welcome back to my channel. So this is an introductory video about the course on the introductory course on modular forms. So this course is for postgraduate students and maybe undergrad students who are interested in this topic can also watch these lectures. I hope they found this to be helpful. So if you are someone who just starting to read, explore this beautiful subject, I hope these videos motivates you to dive deeper into it rather than just losing interest. I mean, these things are way too abstract, so I just hope that while teaching this topic, I provide you both clarity and inspiration. So to start with this video, I will like to point out some quotations, and I like this one so much. So it says modular forms are functions with a soul. So many mathematicians, it's by actually Goro Shimura, and many mathematicians believe that modular forms are living objects. And yeah, so one of the professor I met here in ISER Bhopal, he actually giving lectures on modular forms of half weight and integer weights, and there he mentioned the line, these are living objects in some other world and we are here on earth and these objects might be somewhere else. So yeah, so these are holomorphic functions. If you know about complex analysis, I will put them aside. So modular forms are holomorphic functions, and that actually acts on, they are defined on the H upper half plane. So here H is the upper half complex plane, and Professor Mugersen, as I said, defined these modular forms as living beings living in some other world which we don't understand fully yet. And he dedicated over 4 decades of his life to understand this connection and to understand, viewing these abstract objects as living beings. And I just can only wonder what it must feel like, that one day I wish that I might get closer to these worlds of modular forms and maybe even ask some questions which I wanted to ask guy. So I just hope that one day these living objects I am able to see. And to better appreciate these living objects, it is essential that we understand how they come up in mathematics, how they evolved in the history of mathematics, and in what direction we are actually going. So before moving to the history part of modular forms, I will introduce where they actually exist in physics and mathematics. So modular forms are symmetric functions, you can say, which under some group action. So many of you heard about group action. So here the group will be, in general, you will take SL to Z, special linear group, over integers, and they behave so symmetric. And later in the course I will show you some animations and all, and I will actually suggest you all that you should also look up the graphical approach of modular forms so that you won't actually lose interest in this topic. And yeah, another is which is widely known, that modular forms are central role in number theory, and many of you might heard about how modular forms are used in solving Fermat's last theorem. We will discuss about it. And yeah, another connection is elliptic curves and Galois representation. So these things are way too advanced. We won't cover all these things neither I studied yet about these relations, but see, when you see that these advanced topics like elliptic curves, Galois representation are actually connected by modular forms. So these are advanced topics, right? And for me and for you also, these things act like an inspiration for you. Like there is something more you need to know to fully understand how these abstract looking objects are helpful to understand something more. So you can pursue later on in your life to see the connections. I won't cover this in lectures because these are way too advanced topics. Another is uh, algebraic geometry and its interaction with modular forms via modular curves and modular spaces. So I will tell about this in the end of this series. I will talk about not the mathematics, but how they actually interact with algebraic geometry. And another is very common known, string theory. And even if any of you saw the movie The Man Who Knew Infinity, they were talking about black hole singularity and all in the end of the movie, how the last stage of Ramanujan work was used in the study of black holes and all. And these works are also his work is also used, currently using in string theory and to understand the abstractness of the subject, right? And this is for the general public. I made this quotation, hope you like it. Like, for general point of view, modular forms are one of the most important bridges in mathematics, built over years of work by many mathematicians, not one, much like the legendary Ram Setu. So, unlike Ram Setu was built with a purpose over days, but here modular forms are built over the years, over decades, and it has a purpose. And I hope that by the end of this, or even during the lecture series, I will introduce you the philosophy, how these objects are important in mathematics, and we will now see the history of modular forms. So it actually starts maybe before, but the actual work who was shown up in was from Gauss in the year 1801. Yeah. So he actually introduced the quadratic forms. In some of the lectures, I will tell you, I read about the use of quadratic forms in modular forms in some of the problem I was solving. So before that, I will just tell you, we majorly following this book, and I will tell about the content later on. Just to tell you that I saw the relation of quadratic forms in modular forms, and he introduces the theta function. So this was the foundation of modular forms, how they begin. Not exactly how we see it today, but you can say the origin, the seed was probably given by Gauss, and then the further development made by Jacobi and Einstein, So it's not Einstein, or it's Einstein, and I got a little bit confused in writing the spelling. Okay, so yeah. So their work was around 1840s, and they actually work about on the topic elliptic and theta function. Yeah, more. So they developed the further theory and introduces elliptic function and all. And then comes Poincare, and he defined around the year 1880s, and he defined basically the automorphic form. So modular forms, you can say, are the sub collection of automorphic forms. So he defined automorphic forms and relate the theory with modular forms as. So what I'm trying to say is that what theory we are studying today is not actually exact at that time. They were developing the theory step by step, years over years, and what we see today is a compilation or the modified form of what the theory was at that time. So they just introduces the automorphic form. Poincare introduces the automorphic form, and we later saw that the modular forms are the, you can say the subset, or you can say the subform of automorphic form. And after that, the major impact or the major modern theory of modular forms was given by Ramanujan in the year of 1916, and his work on the Ramanujan tau function and modular congruences was the foundation of the modern theory of modular forms. So his work was on tau function and its proper, you can say, arithmetical properties and modular congruences. We will see in later on about these things. And yeah, and so this was the seed, and we come up with a modern form of the work. And afterward, Hecke was inspired by Ramanujan work, and Hecke developed the modern theory. What we are studying today in the compiled form was actually compiled and further developed by Hecke around 1930s. So he introduces the topics like Hecke operators. I hope it's visible. And develop different levels of modular forms. And then come the Peterson, around the year 1940s, and he introduces the Peterson inner product for modular forms. So we will discuss what levels are. We will see how the Hecke what Hecke operators are and how they behave in different levels, and we also see how the inner product was useful in studying the analytic structures of modular forms. And the inner product is known as Peterson inner product for the modular forms. And the latest work was, there are other latest work like new forms and all, who actually I think arises in the work maybe around the 1990s or early 2000 maybe. But the major latest work was given by Weil, Langlands and other mathematicians who was working on the modularity around the year was around 1960. So the script of this video is on my laptop screen over there, and I am reading over from there and just explaining over here. Modularity theorem. Earlier it was a conjecture, but later it was proved to be a theorem. The essential, the major bridge or the major foundation of the Langlands program. And yeah, so this is all about the history part of the modular forms. Why do we care about the history is whenever so it's one of the important thing I learned over here in the summer internship is that whenever we study some advanced topic, so you should actually know how the theory was developed. It will take time, it will consume a little bit time to read the history and the mathematics. It was the mathematics was developed, but it will be fruitful for in your later career, and it will actually give the clarity why these things are come up in this way only. And I'm actually not read about everything I mentioned over here, but I will motivate you also to just take some time and attend some lectures or seminars. There you will see the history of modular forms and any other topic as well. So I will pause over here. So now we will see the content and references for this course. So I will be majorly following this book, Problems in the Theory of Modular Forms, and we will cover up to, so we will start from chapter 2, modular group, and then we will come up to chapter 2, the third chapter, the upper half plane, fourth with modular forms of level 1, and we will go up to chapter 5, Ramanujan tau function. And then we will skip the 6th chapter. I will just give the idea, we will not cover this. Then we will cover the Peterson inner product, and then I will not follow this book and I will switch to the another one. It's the elliptic curves, modular forms and the L functions, and we will only cover the part of chapter 5, the L functions. And I hope that, I mean, this much, these chapters are I mean, for the introductory course they are more than enough, but I mean they are actually too much for introductory course. But I hope that I will cover up as much I can. So from that book we will cover 2, 3, 4 and 5th chapter, and from this book we will only cover the 5th chapter, and I hope that I will try to do this much. And that's all. Let's meet, and I will just take care of the time. So actually I am consuming way more time in describing all the things, and the video length is getting too much, so I will try to reduce it. And it's my first time teaching a course on YouTube channel, and I am very happy that I am picking the topic that I love so much, modular forms. And I hope that you will learn something. You will get, if not the mathematics, then you will get some motivation for this subject rather than getting bored or something else. Yeah, so see you in the next video. That's it.